So it's my pleasure to introduce Professor Andy Andres, who's a senior lecturer of natural sciences and mathematics at Boston University. He's taught a very successful MOOC online course, Sabermetrics 101, an introduction to baseball analytics, to about 40,000 students on edX. He's formerly the lead instructor and head coach of the MIT Science of Baseball program. And is chairman of the Educational Resources Committee for the Society of American Baseball Research. He's a datacaster for MLB.com at Fenway Park. He scored Game 6 of the 2013 World Series and has a PhD in nutritional biochemistry and physiology from Tufts University. So, apart from the sports angle, I like this topic. I think it fits very well into the Google spirit of avoiding making decisions, from the gut, from intuition, with all the conscious and unconscious biases that represents, and taking a much more data-driven, rational approach. And as we see, that's a big win. So thank you.
Thank you. So this is my cover slide for this talk. Some contact information, but this image is from the MOOC that we designed. And during this few minutes we have together, I want to talk about basically the quick introduction of what I do, why it's important, then a quick summary of why sabermetrics has changed the game of baseball, why analytical thinking has changed the game of baseball, and then try to come up to current technologies and current data that's being used to try to make decisions in the game. And the talk is geared towards the novice. Certainly at the beginning, you might be able to follow things, but if you're a baseball fan or a sabermetrician yourself, maybe you'll appreciate the current technology. So it's been my privilege, through the introduction you heard, I've sort of made this transition from a bench biochemist to a data scientist. And I do lots of work with data, and I'm an educator, so I spend a lot of time teaching folks how to think about data, how to use data to drive decision making, how to think about modeling. So all these things are part of what I do. But I've really made this conscious effort over my career to go from the bench biologist to the baseball scientist. And it's been a lot of different phases. A lot of it actually has to do with the physics and biology of baseball. That actually was my entree into the whole field, was doing anabolic steroids in baseball, that kind of discussion and that kind of research and talks since 2001. But then it's transitioned into sabermetrics and analytics. Quickly, this is a view of my seat at Fenway Park. I get to score the games. I'm in the press box. This is another view when I'm looking down on the field from my seat. And this is my score sheet. I have a different score sheet than a lot of folks, but it has to do with the work I do, which is record every event for all the technology. I record every pitch, every play, in a certain set of code and language. And it's a very intense job. I make the claim all the time that I'm the only person in the press box paying attention to the game, because everyone else is paying attention to MLB at bat, which is what my data generates. So I do all the paying attention these days at Fenway. We generate the box score at Fenway Park. That's just an emergence of technology. The old school version of this was baseball box scores were written up by the official scorer. They don't do that anymore. The official score just calls the game itself. So that's one nice role I have, but it's transitioned to the academic piece here of teaching sabermetrics. And I designed the first course in sabermetrics, just doing baseball analytics at Tufts in 2004. And so we had this seminar of many years teaching Tufts students. But now we've gone into the MOOC format. And one of the things we did right away in both formats, either seminar or MOOC, was talk about the definition of the term sabermetrics. Now, sabermetrics has a funny origin. Here's the origin. The origin comes from SABR, which is the Society for American Baseball Research. And metrics is just a sort of a word to say how to measure baseball. And so sabermetrics is this, it's only been a word since 1981, but Voltaire was the first person to do this, those of you who are philosophers or readers. Voltaire said, first define your terms, and it's really important. When you look at this definition, I'd say this is incorrect. This is not what sabermetrics is. Okay, sabermetrics is not the statistical analysis of baseball data. That's way too narrow a definition for what sabermetrics is. And like a good scientist, I just want to show something and let you see and think about this. Okay, this is slow motion of a pitcher for the Red Sox named Daniel Bard. This is from 2010. And I say Daniel Bard the good because this was a year where Daniel Bard was pitching extremely well. For those of you who are baseball fans, you may remember Daniel Bard a few years ago and how great a pitcher he was that one season especially. Now, if you pay attention to these two slow motion videos, this is the same inning in the same game. These are like 2 pitches apart, okay? Okay, a pitch count, well, 3 pitches apart. You can see the pitch count on the top screen, okay? The first on the left is the Derek Jeter. It's at Yankee Stadium, and it's a fastball. And even though we all know the physics say that the fastball can't rise above gravity, if you appreciate what's going on here, that fastball is defying gravity by having a backspin put on it by the pitcher going up. Now, it's hard to appreciate, but just look how straight the left-hand image is, and then watch how much curve the other pitch gets. Just appreciate the curve on the one pitch and the straightness on the other. So like any trained engineer, scientist, you should be observing this thing, and your natural curiosity would drive questions. You know, what's going on here? These are 2 different pitches with 2 different grips. Both are thrown over 98 miles an hour. Now, baseball fans might know what that means, but these are extremely fast pitches. One is rising against gravity, okay? It's actually defying gravity and going up. And the other is taking this left to right turn, so much so that the catcher can't even catch it. The point is, this is just the time to observe and ask questions, like any good investigation. Now, this is when Daniel Bard was quite good, and he was getting people out left and right. This pitch here to the right was one of those, we call them Bugs Bunny pitches in baseball. It references the old Bugs Bunny cartoon when you had crazy pitches. Now, this is real data. So here is a field of pitches that are yellow triangles. You can sort of see them in here behind the blue squares, which are the changeup. But this pitch right here, these 2 pitches way over here to the left side of that screen where the pitch was that pitch that had that big break, okay? What you're seeing here is data. You're acting like the catcher here, and this is where all the pitches move relative to the bullet spin. The bullet spin is right in the middle of the axis, right in the middle of the 2 big axes there. That would be the bullet spin, the ball just going along its trajectory with gravity. But then you add the spin that the pitcher can put on the ball, and you get different types of pitches. So now this is Daniel Bard the good. This red cloud are his fastballs that rise. The one you saw on the left of Derek Jeter, that's the red cloud. Then buried in there is the yellow cloud of triangles where he's got that pitch that bends. Okay? Now, I'm going to show you, this is when he's good. This is Daniel Bard the good, Daniel Bard the next year, and Daniel Bard the next year. And pretty much after this, he's out of baseball. Okay? Now let me scroll back. Daniel Bard the good, Daniel Bard the next year, his last year. He's tried since then, but he's never made really any appearances since then in Major League Baseball. Now, if you follow the red cloud, you'll see what I mean. This red cloud, if you can picture this is a catcher's orientation. This red cloud is balls that are thrown by Daniel Bard that move a lot from that center point. If you pick where that red cloud is, the center of that red cloud, you can see it move as Daniel Bard is going from good to mediocre-ish to not so good, and then he's out of the game. The point is, this is data sets that we can use to analyze pitching performance, the movement of the baseball. So instead of just watching video and making assessments of how well balls move, we can measure now how the balls actually move based on the spin put on the ball by the pitcher. So this is driving the analytics in baseball. The decision making in baseball can be based on this kind of data now. Now this is older data as in 2007 and 2008 is when this data set emerges, and it's done by video. Okay, two video cameras are trained between the area of the pitcher and the catcher, and they basically do a triangulation of the ball by video analytics, and then they configure the whole trajectory of the pitch from the release all the way to the catcher, just using video analytics. It's called PitchFX. Now, PitchFX is really, really important to baseball analytics. We've actually moved on, okay? But let's go back. We've just gone through a simple little couple minutes exercise looking at Daniel Bard the Good, his actual video, some data showing how his pitches might move and how that might drive some decision making. An objective look at Daniel Bard's performance is what we can see with this kind of data set. So this goes to the definition again. Voltaire was the one who said, first define your terms. Well, sabermetrics to me, and I think most people who really are practitioners would agree with this, it's the study of the game of baseball through observation, by looking carefully. Now, sometimes you can do experiments, but usually you don't. It's more like astronomy that way. You're observing things and trying to figure out what's happening through your observations. That's much more what sabermetrics is. And here's the definition I start off with, all my courses, okay? This is the simplified version of sabermetrics, the scientific and objective analysis of baseball. Much more broadly defined than just looking at the statistical analysis of baseball data. So this is an important part to start. Baseball can be treated as an observational science. You can start thinking about the game and understanding it better. Now, what we've done at BU and at edX.org is develop our course called Sabermetrics 101, an introduction to baseball analytics. And this is one of the big innovations we had in our course. The course is very successful. I could go on about all the data points of why edX loves this course and why BU loves this course and why the students have loved this course. But one of the innovations I kept pushing for was something called the SQL Sandbox. One thing we do really well is teach SQL to novices. And we do it through the SQL Sandbox. We make it very simple to play with SQL right away. And we really do it right away in this course. And we do it right away in my courses in seminar format as well. We take all comers, English majors, non-technical people, and we start doing SQL queries using the SQL Sandbox. So it was an engineering thing to build this little SQL Sandbox. It wasn't tricky, but it really had to look right for the users. That was one of the big innovations we had in this MOOC, in the edX course. This is sort of if you can see this is a simple query, and you can see some of the results. You basically run a query, and you get a bunch of results in a table, and you can even push a button to download the full results. In this case, this query, I think, generated something like 25,000 rows. These are different sets of data for games between 2000 and 2009. So this was one innovation that we found worked very well for our students. In addition, the thing we innovated here was something called tracks. We realized in Introduction to Data Analytics, we'd get some people who were data scientists who were curious about baseball. We'd get some baseball people who were curious about data science. And we'd get different folks with different interests coming into this class. So we created tracks of different topics. We created a sabermetrics track. It was a straight baseball track. We created a technical track where we worked through SQL and R, but a lot of our students already had that done, like maybe many in this room. If they took this course, they actually wouldn't have to take the technical track. We also had a history track. We also had a statistics track. This didn't pretend to be Statistics 101, but it did cover the statistics needed to do basic analytics that we required for the course. So the different tracks was another innovation that actually many other introductory courses on edX have used since then. So that was a nice innovation we also had. The last thing we had was something called the grader. We would take, people would run a SQL query for their problem set, and submit the data set as their answer. And we developed an algorithm to try to grade each answer. And it involved the right number of columns, rows, the order of the columns and the rows, and different criteria to give different grades. But the grader was another innovation for the class. Now, in terms of baseball, really, baseball, when we talk about sabermetrics, we're modeling the game. Okay, just like modeling any system you want to model, you observe it carefully and you try to think about it. So when you think about baseball, you try to understand the game is about winning, but how do you win the game? You win the game with runs. So essentially, when you talk about baseball analytics, you're talking about analyzing runs. How are runs created? How are runs prevented? And that's the model. And that's the key that's the standard that you develop as you build all these models for baseball. Now, fundamentally, when you think about runs, and baseball fans know this, you think about like great players, and they're going to create runs. Like David Ortiz is a great player, and he's got a great batting average and lots of home runs. Well, very early on, and I'm talking a century ago, very early on, people realized the standard metrics for batting performance, batting average, weren't working. There was a problem with batting average, and people recognized this a long time ago. This is a correlation between team runs scored for a whole season. So you basically take a team, you measure their runs scored for that season, and you correlate it with all their batting averages. And now, batting average was the standard metric for hitting performance for the longest time. But even 100 years ago, people said, this isn't good enough. And it actually has a fairly low correlation. Not as bad as this graph. This is the graph I always show when I do these talks, because it's got no correlation. Okay, same x-axis, team runs scored. Take any given team in a season, count their runs scored, but then you try to plot it against the number of outs they record on defense. Now, these should not be correlated because one's offense scoring runs and one is defense preventing runs. Now, there is, if you do it different ways, you can find correlations with these data, but I chose it this way, very low correlation. But I'll show you the final graph. This is a higher correlation for offensive performance. Okay, now this is a fundamental concept in sabermetrics. This is what you do. You look at the game, you observe the game, you think about how to model run scoring. Instead of using standard metrics like batting average, you can take this very simple metric. This is actually quite a simple formula. This is just hits added to walks, H plus BB. So you just measure the team hits and the team walks, and you multiply it by another component, which is total bases, which adds up singles, doubles, triples, home runs, okay, with a little formula, divided by the number of at-bats by walks. So this is a really simple formula, but look how well it correlates with run scoring. So this simple formula was developed in the early 80s, 70s, and it really changed the nature of baseball analytics. Because the analysts who figured this out just did what I've just showed you. They said, people for years have been saying batting average is not a good metric for offensive performance, for modeling the game, for understanding the offensive performance in baseball, but this is. Now, they kept saying this over and over again since the early 80s, and nothing changed. These were outsiders who had no access to the actual clubhouse, to the decision makers. The decision makers weren't listening to the folks telling everybody there's a better way to model the game of baseball, okay? And if you can imagine the market inefficiency. Instead of modeling your team on the best batting average, the players with the best batting average, you can start modeling your team on the player with, sorry for the flashing slides. You can model your team on the player who gets harder hit balls, which is measured by the TB here, home runs and triples and doubles, and get walks. Walks are added here. So this formula, this really, really simple formula, gets at another level of modeling the game more accurately. And the market inefficiency now is taking care of people who hit home runs and triples and doubles and take walks. Now, this market inefficiency is completely closed today. But before the publication of Moneyball, this market inefficiency was wide open. It was first described, like I said, in the early 80s, but it took 2 decades before you got that little, crack in the door into the clubhouse to convince people that this is the way to think about the game, the way to model the game. Now, today, fast forward another decade since Moneyball, there are 150 analysts on 30 teams who this is what they grew up on. Okay, this is fundamental. This is like 2 + 2 = 4 to these 150 analysts. We're talking about a dramatic paradigm shift in an industry. Now, this is just entertainment. We understand that, but it's a dramatic paradigm shift in this industry. That this is the importance of baseball analytics as an emerging discipline, maybe too strong, but a certainly emerging area of study for folks who want to do this kind of work. It's essentially interesting data science around entertainment. So let's go back to another set of data. Another set of data emerged in 2008. This is John Lester from 2007 to 2014. These are all his pitches. Now, remember what this is again. I'm going to try to describe this carefully. This is the catcher view. Okay, you're the catcher. So John Lester is the pitcher, and he's a left-handed pitcher, and he's throwing pitches to you, the catcher, and he's got 5 different pitches. Okay, the 4-seam fastball is the one that's going to rise the most. So that cloud of black circles is the one that's the highest velocity. Okay, that's the fastest pitch. Now you can see he's got balls that the sinker, this gray cloud here, that actually moves a little different than the fastball. These are the 2 pitches you saw by Daniel Bard. The fastball was the one on the left to Derek Jeter by Daniel Bard, and the sinker was the one that curved so much left to right. Now for John Lester, he's a left-handed pitcher. It's going to curve the other way. It's going to curve from right to left because he's lefty. So when he throws his 2-seam sinker, it's going to move this way. Now he's got 3 other pitches. He's got his curveball, which is going to spin down, and that's the yellow cloud here. He's got the changeup, which is a whole nother pitch altogether. It's meant to slow down, and you can see how it's lower on the graph. It's a lower velocity pitch, so he grips it differently, and it's actually a slower pitch. And then he's got another pitch that he's spinning the other way from the sinker. Okay, he calls it a cutter, a slider. These are different names for very similar pitches that go the different way than the classic sinker pitch. The point is, if you don't know baseball, that's fine. The point is there's a pitcher grabbing a baseball that's going to spin in air, and he's doing this on purpose. So we can collect all these data and look at John Lester. Now, one data point of one pitcher doesn't matter much, but what if we compare John Lester now to another? This is another left-handed pitcher with the same 5-pitch repertoire. Okay, this is Jose Quintana. Now, what I've done is I've manipulated the images so the scales are the same, and I'm going to go back and forth. Now, you should understand that one pitcher is throwing it faster, okay, and one pitcher is throwing it with more movement. And this is the way now to measure pitching, okay? We're not going to measure ERA anymore, which is a fundamental measure of pitching performance. Now we can take these data and say who moves the ball better, who moves the ball faster. Now there's a key piece missing here in this data set right here, which is how accurately they can throw it, their placement of the pitches over the strike zone. But just on the skill set of these 2 pitchers here, Lester has more velocity and more movement of these pitches. These scales are exactly the same. And so now this is just to show you we have another way to measure pitching performance using technology and new data. Okay, so this is using the PitchFX data set and understanding the different pitch types and understanding how these pitches move as a measurement of value of pitchers. Now, I throw this one in here just because it's fun. Has anyone ever seen this before? This is Todd Frazier. Todd Frazier now actually plays for the Chicago White Sox. This is when he was on the Reds. If anyone's from New Jersey, he's from Point Pleasant, New Jersey, the Jersey Shore. No one, Jersey Shore? Okay, fine. But watch. If you look carefully, it's pretty obvious his right hand, watch his right hand, is off the bat at bat-ball contact. But if you look carefully, his left hand is too. He has essentially thrown the bat at the ball, okay? He's throwing the bat at the ball. Now, if you've ever played baseball, the coach would never tell you to do this. This is not classic baseball. But what's really interesting here is the physics. We can use this as a physics example of understanding bat-ball contact, okay, the mechanics of this. But beyond that, this was a home run. Okay, he hit this ball about over 400 feet. Okay, so he's throwing the bat at the ball and it goes 400 feet. So this is the introduction to understanding a little bit more about home runs. Okay, home runs. So here is a list of all the different teams and their ballparks. It would probably surprise you if you're a baseball fan. If you understand this and you're a baseball fan, it would probably surprise you to see that last year the most home runs were hit by the games played in Baltimore at Orioles Park. Most people who are baseball fans might say, oh, that's Coors Field. That's where there's a high altitude and balls just travel farther. But no, most home runs were hit in Baltimore. The least home runs were hit in San Francisco. Okay? Now, this is just a rank order listing of the home runs that occurred in every park. But as we start understanding home runs, as we transition into understanding this is one data set that we can start thinking about. Now, here's another data set. This is actually really interesting. This is by Greg Rizarbeck. He's actually a Red Sox analyst now. What he did is took video of every home run ever played. He had like a package and he could watch videos of all games and he would find every video of a home run since 2006. So this is yeoman work because there's about 5,000 home runs a year, okay? And he would find where it landed in the ballpark. And he had 3D reconstructions digitally, reconstructions of all ballparks. And he would time on his video bat ball contact and then where it landed. So he has a time in the air, a position where it landed, and he actually got more sophisticated near the end and put in weather in there and he put in wind in there. He talked to the physicists about batted ball flight, understood better about the potential batted ball flight moves here that are typical for righty-lefty, lefty-righty stuff. And he modeled various components. So this data set is just looking at home runs in 2009. Okay, so this is the cloud of all home runs graphing their batted ball velocity, how hard the ball was hit. Now, Greg calculated this. He calculated the batted ball velocity based on hang time in the air and the distance, okay, and a few other parameters. He also determined the launch angle. Okay, so he is estimating both launch angle and batted ball velocity just by looking at video, okay? A lot of work, but probably a big error bar around the precision of what this actually is because he's doing a lot of formulation to get these two sets of numbers. But clearly, it should show you something. What's the average? He's not too far off. This is pretty good modeling. But it tells you the average batted ball velocity for a home run is about 103.6 miles per hour. Off the bat, home runs average this. Now, there's a big range. You can see some home runs were, pretty weakly hit. Those are probably things like pop-ups at Fenway Park that scraped the foul pole or something. So it's a weak hit that might just be a home run, but some were hit quite hard. You can see the outliers on both sides. And then you can see the launch angle. Most people, when they think about trajectories that you learn in Mechanics 101, you think 45 degrees is the best. Well, in baseball, it's not. Data clearly shows you here The launch angle is about 28. The average, now the range is anywhere from 43 down to 18 or 19. When you're hitting an 18 or 19 launch angle, that's a line drive. That's a low trajectory. And then, of course, you've got the 40, almost 45-degree trajectories. But the typical home run is much more like 30 degrees. Now, this makes sense when you understand the physics and the backspin, okay, of a baseball and how balls move in the fluid of air. So you can explain this by looking at the science quite easily. But this was an important little data set to understand. Most people wouldn't get this right away. Now, also in 2009, we have another data set that looks at all batted ball events. This is just April 2009, but it's another technology just using video analytics. Remember that video analytics of PitchFX where you basically reconstruct the trajectory of the pitch with high-speed cameras in this area between the pitcher's mound and home plate? You can do the same thing with the batted ball. When the ball is hit, you can watch the trajectory through those camera areas. Now, it wasn't a great technology. It actually had lots of errors. But this data set tells us a very similar thing. Okay, what we're showing here in different colors is a fly out, which is a ball hit in the air. That's different than a pop-up, which is sort of a ball hit in the air, which is closer to where the batter is. Then there's line outs and ground outs and singles, doubles, and triples. For those of you who know the game, you understand these clearly, but you can sort of see where these clouds are. I've reduced this cloud into different points, average points for each of those 8 events. These are the outs, the pop out, the fly out, line out. And if you understand the graph here, looking at the velocity versus the launch angle, which is what we showed before with the other data set, you can sort of see why that might curve. You understand the game, or what a liner is, what a pop-up is. You see why they might have different batted ball velocities and trajectories. But this is the single. The double and the triple are very close. They're actually very similar batted ball projectiles off the bat. But then here's the home run. Okay, the home run is singularly different. You've got to hit it harder, and you've got to hit it at the right launch angle, the right trajectory, the right bat, the angle off the bat. So this is another data set showing very similar thing. Another complete different technology. Instead of looking at video, which is what Greg did, seeing where the ball landed and the time in the air, this is looking at video reconstruction of a high-speed camera of the initial flight path of the ball. Okay? Now we can go to another data set. We have a third data set. This is actually not the third data set yet. Greg's data set looking at the trajectory, flight time, and landing spot gets this data set for 2015. Okay? So you can see it's very similar. It's about 30 degrees launch angle, and it's about 104, 103 miles per hour off the bat. These are home runs again, okay? Very specific hits, and they fill the same cloud. So we're getting a sense now of what a home run looks like. So if you could read the initial batted ball velocity and you see about, over 100, and you see a launch angle in the area 20 to 35, 40, you could say home run, you're probably going to be pretty close. This is definitely what a home run requires to be the ball to be hit over the fence. So there's new data now, and it's using radar. Instead of using video, there's radar in the stadiums. This is radar data. Now this is a little different. It's not the same sort of axes anymore. But what we have on the bottom is batted ball velocities, okay? But these are average. Each of these points represents one player in 2015, just one player. And these are the top 150 or so players, and I chose 150 mainly because I wanted to get the full-time players. Players who played the most would be determined by their management to be the best players performing to great runs. So this is all the different players, okay? So we've got their average batted ball velocity. It turns out when you take the top 150 players, you get you get 300 events. So this is an aggregation. Each of these points is an aggregation of 300 batted ball events during the year 2015. So the top 150 batters, 300 batted ball events. In other words, they hit the ball, okay? Now, when you take the average velocity, you get this huge range. The average ranges from about 82 all the way up to 94, 95. That is a big range of batted ball velocities. This is a distinguishing characteristic of a batter. It really is a distinguishing characteristic of a batter. You can really determine what's an average player who's playing full time. These are full-time players. You can sort of pick that group in the middle, the average. And you can pick that group at the bottom. And you could call them, the weaker hitters. And the ones at the top are the stronger hitters. Now, who's a baseball fan that in the audience here wants to take a guess at who might be a weaker hitter and who might be a stronger hitter? Anybody a baseball fan enough to want to guess that?
Sure, weaker hitter is Billy Hamilton, and stronger is Giancarlo Stanton.
Stanton and Hamilton, good. Good guesses. Ooh, yikes. That was just a home run, see that? Any other guesses? Any other baseball fans who want to hazard a guess?
Jose Iglesias, Mike Trout.
Good, good. Actually, you're not hitting any of the leaders, by the way, or the followers, the bottom group. Okay, let me just show you. Now, the other part of this here is batted ball distance. It also, you can see how there's a slight correlation between batted ball velocity and distance. There's something there. You can sort of see that the weaker hitters don't hit it as far, right? Now, so who's the cluster at the bottom there? The cluster at the bottom are 4 players. Burns from Oakland A's, Ben Revere, Ichiro Suzuki, and Dee Gordon. And Dee Gordon, I don't know if you follow this stuff like I do, but Dee Gordon just got suspended for anabolic steroid usage, which is, he's way at the bottom. I don't know what's going on there. It doesn't seem to be hitting the ball hard is not part of the equation for Dee Gordon. But on the other side, these top 5 are Trumbo, Bautista, Cruz, Ortiz, and Miguel Cabrera. Now, very close, I'm sure Mike Trout's very close. I'm sure Stanton is very close to the top of this group here. And I'm sure the others you mentioned are at the bottom. The point is, this is now, I'm going to go out on a limb and say this is the right way to think about batting power. And one of the key things, this is 2015, right? You're a smart GM. You might say, look at that list at the top. One of those things is not like the other. Mark Trumbo. Mark Trumbo was a free agent. And one very smart team signed Mark Trumbo. And Mark Trumbo is having a great year this year. Now, small sample size. There's not necessarily a cause and effect here. But the point is, this might be a new way to really understand the value of batters. Remember what these points represent. For Mark Trumbo, that's over 300 batted ball events. And he hit it harder than everybody in baseball except 4. 4 guys who anybody would list as a power hitter who hits it hard. Miguel Cabrera, David Ortiz, Nelson Cruz. Okay, these guys hit the ball hard. We all see it. You can observe it. Now, you see Mark Trumbo hit it hard too, but it might be a surprise to see him that high on the list. Question?
Willie Montpena would have shown up on the right side of most of these. He was clearly...
Probably, yes. I agree. The observation was Willie Montpena probably would fit on the right side of these graphs. This data set doesn't encompass Willie Montpena. This is 2015, 2016. This is when we put radar now in all baseball parks.
If Trumbo, let's say Trumbo and Pena had both on the list, the smart GM would have signed Trumbo, the loser GM would have signed Pena. But there wasn't any evidence to indicate that one was better.
Fair point, but I think there's more to it than just this, for sure. Okay, so this isn't the end of the story or the whole story, for sure. But this is a real new look at the performance of players. A new look at performance of players that we didn't have before last year. Okay, these data are now available. We can look at that. Now,
Is this data all available, like, is this all open source and I can go and download all this?
if you ask nicely, the question was, is the data publicly available? The answer is yes. If you ask nicely, I can tell you where to find it. It's not hard to find. Just Google StatCast and you'll find it. But this is the radar. And if you go to Fenway Park anytime, just look behind home plate, mount it on the press box, look for this little box right here. This is the radar that covers the whole field, that's measuring the pitch, okay? Measuring the trajectory of the pitch at 40,000 times a second. And it gets the actual release point. It actually can determine the three-dimensional components of the actual release point of the pitcher. Not just guess it, which with the previous technology of extrapolating data points through video analytics. Radar gets the release point, the exact spot where it's released. It can measure seams on the baseball. It's that precise. And it can obviously see the pitch trajectory, recreate that. Now it can also recreate the hit trajectory, and that's where we're getting these data sets from. The velocity of the hit and the distance of the hit and the trajectory of the hit and the spin of the hit and the spin of the pitch, all measurable now because of radar. Now, we also get every throw made. Okay, so you bat the ball into play, the fielder gets it, and they throw it to another player. All those throws are now measurable. You can measure the trajectory of every single throw with this technology. So we are at the leading edge of a whole new set of analytics like this. Now, there was a great question about, is this the end, be all and end all? Is Miguel Cabrera the best hitter in baseball? He's one of them. He's not the best. But when you model the game, when you model run scoring, when you're the objective analyst now, you have to take this data into account. You've got to start adding this new technology to your model to better understand offensive performance, to better understand where runs come from, to leap beyond the idea of understanding just what batting average is, contributing to offensive performance and run scoring. So radar is key. There's another component here, though, too, which is really important. These are 6 cameras, and I took a photo at Fenway Park, just wandered around and took this picture. Each of the sides has 3 cameras. The one on the right-hand image is 3 black rectangles next to a white sort of, that's actually a radar gun to measure pitch velocity. But that's 3 cameras there. And on the other left side there are 3 cameras mounted, 3 on top of one another. If you go to any major league ballpark, it might be fun to, since you're technology oriented, you might try to find the radar system and the 6 cameras, because they're in every major league ballpark. They're actually in a lot of minor league ballparks, because what teams have found out now is it's not just measuring the major leagues. You want to do it for the minor leagues too. You want to install these systems so you can see which batter's hitting it the hardest in the minors, to either trade for them or to promote them. It really is getting more and more pervasive, this set of technology. So the cameras here measure player movement. That's not measuring ball movement. If you've ever followed football, soccer, or other moving sports, if you watch the World Cup, you see how they track players. And they track players through video. They don't need little trackers in their shoes or anything like that. You can just watch, you can determine where the player is by video analytics. Chiron Higo is a European company that does this very well. Sports Vision is an American company trying to do it. But Chiron Higo was hired to do it for baseball. And the technology tracks the movement of all the umpires, all the coaches, all the players, all the runners, the batter. Everybody moving on the field is now tracked through video analytics. So now we have another set of data measuring player movement all over the field. And this is important now too, obviously, if you want to measure defense. And if you want to measure offensive performance, base running or batter times to first. These are all things that are important to measure if I want to better understand offensive or defensive performance in the game. So emerging now are big data sets to help us better understand the value of each and every player in the game of baseball. Now, when they announced this in 2014, that this was going to be coming to Major League Baseball, they also made the announcement that this is 7 terabytes of data every game. Now, that's a lot of data. Now, Google laughs at that. They're like, whoa, 7 terabytes. I use that in my hip pocket in the morning. Oh. But you know what? This is actually a big data set for baseball. Relative to what other data sets we've had in the past, even though baseball was considered data rich, this is actually really emerging into bigger analytics of big data sets. And so a lot of time has been spent by the very smartest cutting edge teams to parse through these data to get the right data they need. A lot of time has been spent also by Major League Baseball to help teams do this. There's a lot of folks working in Major League Baseball to get through these data, to boil it down to really important information that the teams can use. And that also might be useful for the fans of the game. It might be fun for fans to see these different things. So let's move on to other things. Let's move on to another way to use these data sets. I only have a couple more slides, but this is interesting. This is David Ortiz in 2015. What's shown here is his batted ball location. Okay, most people probably wouldn't have guessed that David Ortiz, most of his batted balls go right to center field. If you're a fan, you know everyone's shifting on David Ortiz. But David Ortiz is learning to hit it straight up the middle mostly. So you look at the heat map, and that's most of where his hits are landing. Okay. Now, if you look at Jose Bautista, if you know anything about Jose Bautista, you can see him. He's a pull hitter. You look at his heat map, he's a right-handed batter. This is a demonstration of the field, and you can see most of his hits are pulled. Here's another graphic of Jose Bautista, 28 to 2015, all his home runs. He's a pull hitter. If you understand the game of baseball, he's pulling everything to left field. This is Ryan Howard. Now, he's a left-handed hitter. He pulls the ball, okay? Now, those of you who are Red Sox fans might know who Xander Bogaerts is. Xander Bogaerts, I see some heads nodding. Xander Bogaerts is the shortstop for the Red Sox, and he doesn't hit a whole lot of home runs, but he's got an interesting profile here. And this actually goes along with your observation. If you watch a lot of baseball, you'll see Xander Bogaerts is much different than Jose Bautista. They're both right-handed hitters. These are many batted ball events. This is not just like one data point. These are a lot of data points of where their ball lands when they hit it. Compare this heat map. And look, one big thing to compare is how close it is. Okay, he doesn't hit it far. Okay, it's closer to home plate, which is the bottom of those 2 black lines. Here's Jose Bautista. Jose Bautista, his heat map extends a lot further, and it's certainly pulled towards third base, left field, compared to Xander Bogaerts. Okay, he's hitting it opposite field. So very interesting set of heat maps. The last thing, I'm going to run through these slides quick. If you care, there's something called catcher framing. But what people don't understand is batters have a strike zone. In other words, you might understand that umpires have a strike zone. Some umpires, if you know the game, might have a wider strike zone. Some umpires might be tighter. What people don't understand as fans is that batters have a strike zone. They really do. When you understand the strike zone, baseball analysts who study the strike zone know there's 4 parts to the strike zone. Each pitcher has a strike zone. Each batter has a strike zone. Each umpire has a strike zone. And each catcher has a strike zone. They all impact that called pitch being either a ball or a strike. Let's do this. This is Jose Bautista. He's a right-handed hitter, okay? Let's compare him to Mike Trout, another right-handed hitter. These are all data from 2014 through 2016, okay? So this is Bautista. Here's Trout. Bautista, Trout. So these are 2 different guys with 2 different strike zones. You can appreciate the difference in the red field, okay? Now, let's go to a left-hander. This is David Ortiz. This is his strike zone. Bryce Harper, another left-handed hitter. Okay, another great left-handed hitter. Look at the difference. Okay, there is differences here, and this is subtle. This is a subtle difference between batters that impact the strike zone. So, cutting-edge analytics that aren't really being published even in the public, but what the teams are doing, what they're doing is they're better understanding each batter's strike zone, each umpire's strike zone, each pitcher's strike zone, each catcher's strike zone, and they're emerging now like who's pitching, catching today, who's the umpire today. And they can actually make this part of the scouting report to help inform either pitchers, catchers, or batters what advantages there might be to winning the game that day. Okay? So this is the kind of thing that's new. Old was this idea of let's value walks, let's value the home run. New is using technology and data to drive decision-making in real time to understand better small advantages that might help you win games. So look, I understand this is entertainment. I understand this is fun and games. But this is sort of an analogy in a way to a lot of things going on in real industry, real decision-making in real business and real things that might matter a lot more than baseball. So we can talk about this baseball story and how it kind of relates to this emerging study of anything we observe, anything, and I use anything literally because we've done it with baseball. So anything can suffer a close observation, thoughtful questioning, trying to understand it better, gathering data to be objective about what you're trying to answer. So we've done that with baseball. I think it can be done with anything. And I thank you for your time. If you have any questions, I'll be glad to answer them.
Hi, thank you very much. What are some of the teams that you think are the most cutting edge in this stuff?
Cubs, Rays, Red Sox, Nationals, Yankees are pretty good. I would say Astros. I forgot the Astros, yes.
Sorry, is that a function of how much they're willing to spend, or the actual people they have doing the analysis that produces the better results? You would think every
Some it's spending and some it's people. It's a mix. Astros, it's actually people. Rays, it's people. Red Sox, it's a combination of people and money. Cubs, it's mostly money, but a lot of good people.
So it seems like observationally watching a game, whenever anybody really hits a triple, it always seems like they hit a double and the fielder really screwed up, but it wasn't close enough to really be called an error. And given what your chart showed earlier, that they're basically the same kind of hit, is that your observation as a scorer too, or? Yes.
I don't make the hit error decisions. I just record everything when I'm working at MLB. But I agree with you. From what I see, these are hard hit balls that rattle around outfield fences, and you just can't call errors on certain plays. It's if they're making ordinary effort, okay, and they screw up, that's when you give an error. But if it's like some crazy thing that happened, you can't give errers to that. So.
Yeah. I mean, even when they like fall over, but like, you know, they fell over not within 5 feet of the ball. So this is being recorded, so I better watch what I say. But I have a lot of stories about how the sausage is made in official scoring. Yes.
The data you were talking about collecting, is that available to all the teams equally, or do some of them have private data that they're adding into this?
This data set is for every team. Every team has access to it. But that doesn't mean other teams aren't adding their own data. There's other data providers out there that are trying to sell data to teams, and some teams buy it. Some teams are thinking about data a little differently. They're gathering data, they're spending money to get data in low minors and other places too. So each team is a little different, but this data set using radar and video analytics is open to all 30 teams.
So when academics discover things, they publish them. In this case, finding a new metric that works really well is probably something you want to keep proprietary. Do you guys lean more towards that or more towards sharing with each other?
I think the industry is always looking for the market inefficiency and for that advantage. Now, this isn't as a clear-cut advantage as some other industries. If you make a better widget and you cut the price in half, you will make more money. That's a measure of that system. In this system, you want to measure it by, say, World Series victories. By getting more value from your players because of some metric about how hard they hit the ball, that doesn't guarantee a World Series victory. But it certainly would be a slight improvement. And it is a market inefficiency. In terms of academics and publishing, I think there is the outside world, and I'm actually part of the outside world, where we actually look at data and we try to analyze it and publish it on the web so everyone can see it. Then there's other data involved and better models involved because of the richer data sets in the clubs, and that's not something we're privy to. The outside doesn't see that. It's very proprietary. There's some crosstalk between teams, but not much. They usually hold information pretty close to the vest. But I'm on the outside, so I just try to look at data that I can find and analyze it.
Hi. Two questions actually. So at the player level, how much are teams sort of sharing any data points? So one thing that stood out was you said they put the shift for Ortiz, but he sort of hits to the middle. Do they share that with their players at all and say hey, you shouldn't necessarily shift, and build in a player by player strategy? Are teams doing that?
Yes,
Right?
absolutely.
Okay.
If you watch baseball a lot, you'll see how every at bat shifts the defense. Every new batter coming up, they'll always have a different move. Even within pitch counts, they'll shift. They'll move players around in pitch counts, and so they understand the different pitch counts and the batters impact where you should be on defense. It's that granular.
Cool. That's pretty interesting.
No, I agree.
And then the other question I had was, it seems like this would be pretty good information for video game developers to have. I'm curious if you share a lot of this and if they incorporate it well or not well.
The data I have is freely available. Now, I'm not the best web scraper in the world. If one of you want to have a cup of coffee and I have a couple web scraping questions, I'd love to. I have a couple of things I need to get better at, but I don't know of any game developers using this, but it's freely available. In other words, they can find these data sets to better do whatever gaming they're designing. It's out there, and I'd agree with you. If I were a game designer, I'd really want to model the game a lot better, and these data are out there.
When I saw the graphs about Daniel Bard's pitching, two things jumped out at me, and I wasn't sure if you had a comment on them. One, there's this old saw that command is everything for a pitcher. If you don't have command, it doesn't matter how fast you throw, and if you have command, you can do well. And then there's the other one, which is that it's all about variance. So if you lose fastball velocity, but your changeup can still be overpowering if your changeup also slows down, like Keith Foulke or Trevor Hoffman. But when I look at that graph, one thing seems to hold up and the other one doesn't. And I'm not sure if you had a comment on that.
On Daniel Bard?
Yeah, because he seemed to retain a lot of variance from 2009 to 2011, but he clearly lost almost all of his command. And
The observation is he lost his command. If you watch what he did, he just started walking batters everywhere. But that's not what this data set actually shows. So what this is trying to represent is the movement of the pitches, and that's his ability to spin it.
Yeah, but command is like when you're a pitcher, you're expecting the ball to behave a certain way. I mean, when I look at a graph like this and I see a tight cluster, it means that the pitch is predictable. And so the pitcher can command the pitch by, assuming that it's going to go a certain way. And then if you go two slides ahead, as the fastball graphs start to spread out, it means that he's walking players, he's lost command. But he still has a lot of variation. I mean, his slider is actually breaking even more than it was before.
Yeah, I think this is not representing the strike zone and command. I could do another graph which shows you how well he's hitting his spots. This is a measure of movement of the pitch. Okay, so it's not we're not really getting is he hitting his spots. So the cluster, you're right. If I were getting at command another way, I'd look at how well he's clustering around a certain band where I want the pitches to go. But you mentioned something really important. You mentioned this idea of sequencing, the idea of not being consistent, not showing the same thing. Advanced analytics today, and there's real teams who understand this that others don't. This idea of sequencing, this idea of understanding a pitcher-catcher being in sync about a certain set of pitches, different kinds of pitches, different locations to different batters, and how that's working. So sequencing is really important, really, really important. This graph is showing more his ability to spin the pitch. Something happened to Daniel Bard after 2010, and it's sort of a mystery because he had such talent. It wasn't age, it wasn't injury. Something happened where he just couldn't spin it as well. He couldn't spin the pitches as well. Yes, 2012 he started to start.
Yeah.
But it was actually his choice. If you go back and look it up, he wanted to start. So the very interesting scenario here. Daniel Bard's someone's going to write a great book about Daniel Bard someday. Maybe one of you. Yeah.
So you showed there's a huge difference between the stadiums and the number of runs. Do you have an idea what's going on there? Are these smaller stadiums or like these?
Smaller stadiums, but the biggest effect is the players they have.
I see.
I mean, Toronto was number 4 on that list.
Yeah, Toronto was up there, Baltimore was up there. These guys, they have players who hit a lot of home runs.
Okay, yeah.
But it is also the park, trust me.
So
Fences in, altitude up, balls, more home runs. But the players you have also determine that. It's one of the lower teams was Atlanta. Atlanta's I don't know if anyone's a Braves fan, but Atlanta is this is a season where they're rebuilding. They have weaker hitters than they would like, I'm sure. And so they have low home run rates at their home park.
Do you know if anyone is trying to design a ballpark so that it would be more home runs? Is that allowed with the sport?
I think people do that.
Yeah.
I think they do because there was a famous advertisement by 2 pitchers, Greg Maddux and Tom Glavine from Bill Ricca, and the advertisement was their pitchers and all the fans were appreciating all the home run hitters, right? the phrase was everyone loves the fly ball. So it is home runs and runs. I think people thought that was a way to bring fans back, more interest in the fans. Thank you for your attention.